Welcome back to the channel. The exam asks about NoSQL, caching, and warehousing, DynamoDB, ElastiCache, and Redshift in sneaky ways. Today we build the instinct to see through them. By the end of this video, you'll be able to look at any Amazon Web Services database scenario and instantly know whether it belongs on DynamoDB, ElastiCache, or Redshift. Here's the wrong mental model most engineers carry in: that these three are competing options where you pick the best one. They're not. They do completely different jobs, and confusing them is exactly what makes someone pick a data warehouse for a transactional workload and watch their bill triple. Today we'll cover three engines: a serverless NoSQL key value store, an in-memory cache, and a columnar warehouse, and the one distinction that sorts almost every question between them. In episode 21, we covered the managed relational engines, Amazon RDS and Aurora, the workhorses that run a production application's structured data. And back in episode 3, we mapped out the global infrastructure, regions, availability zones, and edge locations. Now CodeGorillas picks up a gaming client who wants a real-time leaderboard, and here's the thing: relational isn't the right tool anymore. They need three different non-relational engines, and that's exactly what we'll sort out today. Before we get into the engines, let's pin down 5 terms you'll hear throughout this video. OLTP, online transaction processing, is many small, fast reads and writes on individual records. That's what runs a live app. OLAP, online analytical processing, is the opposite: a handful of complex queries that scan enormous datasets to answer business questions. A NoSQL key value store is a non-relational database that looks items up by a key, built for speed instead of complex joins. Columnar storage keeps each column together on disk, so an analytics query reads only the columns it needs. And an in-memory cache keeps hot data in RAM for microsecond access, sitting in front of a slower database. So CodeGorillas sits down with the gaming client, and 3 requirements land on the table. First, a real-time leaderboard, read and written by millions of players, where every lookup has to come back in single-digit milliseconds. Second, the product team wants weekly revenue analytics across years of game history, trends, cohorts, regional breakdowns. And third, the very hottest data, the real-time top ranking, needs to be served instantly, every single time. Now, you could try to force all 3 onto one relational database, but it would buckle, because each of these jobs has a fundamentally different access pattern. The right answer is 3 different engines, each doing the job it was built for. Here's the single distinction that resolves most questions in this space. Think of a cash register ringing up one sale at a time all day long. That's transaction processing, OLTP, and DynamoDB lives there. Now think of the quarterly business review, where someone asks how sales trended across every store this year. That's analytical processing, OLAP, and that's Redshift. You'd never run the quarterly review on the cash register, and you'd never ring up customers on the analytics dashboard. DynamoDB runs the business, Redshift analyzes it, and ElastiCache makes the hot parts instant. Picture a busy restaurant. DynamoDB is the kitchen, taking individual orders fast and at any volume. That's the transactions flowing in. ElastiCache is the heat lamp, keeping the most ordered dishes ready to grab instantly, so nobody waits. And Redshift is the accountant who, at the end of the week, pores over every single receipt to figure out which dishes actually made money. The important thing here is that these aren't competing for the same job. The kitchen can't do the accounting, and the accountant can't cook. Each one does work the others simply can't. Let's lay the 2 sides side by side. On the left, OLTP, many small, fast transactions, reading and writing single records, running the live app. That's the cash register, and DynamoDB is the engine. On the right, OLAP, a few complex queries that scan huge datasets to analyze the business. That's the quarterly review, and Redshift is the engine. When a question describes fast key-value lookups or real-time reads, you're on the left. When it talks about business intelligence or analyzing trends across years, you're on the right. Get this split right and most of the work is already done. Let's start with DynamoDB, and this is one phrase worth memorizing word for word. It's a serverless NoSQL key-value and document database with single-digit millisecond latency at any scale. Break that down. Serverless means there's no infrastructure for you to manage, no instances to size, no patching. NoSQL key-value means you store and fetch items by their key, fast, and single-digit millisecond at any scale means whether you have 1,000 users or 100 million, the response time stays flat. That phrasing matches the exact wording from the official DynamoDB product page, so let it stick. And this isn't my paraphrase, it's straight from the DynamoDB product page. Amazon Web Services describes it as a serverless, fully managed, distributed NoSQL database with single-digit millisecond performance at any scale. Notice the words they chose, fully managed, so Amazon Web Services handles the operations, distributed, so it spreads across infrastructure automatically, and at any scale, which is the promise that latency doesn't degrade as you grow. When you see those words in a scenario, your brain should jump straight to DynamoDB. So where does DynamoDB shine? High-velocity operational workloads, web, mobile, gaming, and Internet of Things. Our gaming leaderboard is a textbook fit. Player scores read and written millions of times per second, with flat latency, and the scale here is genuinely staggering. In production, DynamoDB serves more than 10 trillion requests per day and peaks above 20 million requests per second. But here's the boundary you cannot forget. It is strictly transactional. DynamoDB is never the answer for analytics or reporting. The moment a question asks DynamoDB to analyze trends, that's the wrong tool. DynamoDB gives you two capacity modes, and the choice comes down to your traffic shape. On-demand is pay per request with no capacity planning at all. It's the recommended option, and when you create a table in the console or through the SDK, it's the default. One thing worth knowing, if you create tables through CloudFormation instead, the default is actually provisioned unless you explicitly ask for pay per request. On-demand is the right call when traffic is unpredictable or spiky, because it absorbs sudden surges far better. Provisioned, on the other hand, is where you reserve hourly read and write capacity units up front. It's cheaper per request once you're at steady, predictable scale, but it requires you to forecast your workload. And there's a sting in the tail. If you exceed your provisioned capacity, DynamoDB throttles instantly, with no grace period and no automatic overflow. Underestimate, and your users feel it. Now here's the part people get wrong. They assume one capacity mode is faster than the other. It isn't. The developer guide says it plainly. Tables using on-demand mode deliver the same single-digit millisecond latency and the same service level agreement that provisioned mode offers. So the choice between them is purely about cost and operational effort, never about speed. Spiky and unpredictable, reach for on-demand. Steady and forecastable, provisioned saves money per request, same latency either way. Quick checkpoint before we move on. DynamoDB is your serverless NoSQL store, single-digit millisecond, transactional, that's OLTP for capacity, on-demand handles spiky traffic, and provisioned saves money on steady, forecastable load, with identical latency between them. Now, even single-digit milliseconds isn't the fastest you can go. For the very hottest reads, there's another tier, and that's the cache. Meet ElastiCache. This is a fully managed in-memory data store that delivers microsecond latency, that's 1,000 times faster than milliseconds. The key insight, and the one that keeps you out of trouble, is that ElastiCache sits as a layer in front of a database. It absorbs the hot reads so they never touch your slower database, but it is never the system of record. It does not hold the durable truth. Whenever a scenario mentions microsecond latency, an in-memory store, a session store, or reducing database load, ElastiCache is your answer. Here's the shape of it. On the left, your application makes a read request. That request hits ElastiCache first, which serves hot data back in microseconds. Only when the cache doesn't have the item, a cache miss, does the request flow through to the system of record behind it, your RDS or DynamoDB database. So the cache absorbs the repeated, popular reads, and the database only sees the misses. The result is microsecond latency for hot data and a database that's been shielded from a flood of identical reads. ElastiCache gives you two engine choices, and the keywords separate them cleanly. On the Redis side, you get persistence and replication, complex data structures like sorted sets and publish-subscribe, and failover across availability zones and regions. That richness is exactly why Redis is ideal for leaderboards. A sorted set is built for ranking and for durable caching. Memcached, on the other side, is deliberately simple, with no persistence and no replication. It's multi-threaded, so it spreads across cores, and it offers plain key value only. If a memcached node fails, you warm the cache from scratch. So the rule is, persistence, replication, or complex data types means Redis. Simple, multi-threaded, throwaway caching means memcached. One quick currency note so you're not caught off guard. In October 2024, Amazon Web Services launched ElastiCache for Valkey, and Valkey is now the recommended default engine for new clusters. Valkey is a BSD licensed fork of Redis, same protocol, same commands, same client libraries, so migrating is essentially transparent, and it prices roughly 20 to 33% lower than Redis on ElastiCache, which is a real saving. For the certification itself, the canonical framing is still Redis versus memcached, so that's the comparison to anchor on. Just know that in the real world, Valkey is the modern default, not Redis. There are two main ways to fill that cache. Cache aside, also called lazy loading, works like keeping a notepad next to the phone. When someone asks for a number, you check the notepad first, and only if it's missing do you look it up in the big directory and jot it down. So the app checks the cache first, and on a miss it reads the database and populates the cache. The upside is you only ever cache data that's actually requested. The downsides are that a miss costs 3 round trips, and without a time to live, the cache can serve stale data. Write through is the opposite habit. Its trade-off is that you might cache data nobody ever reads, since you update both the cache and the database at the same time on every write, like updating your phone contacts and your paper address book together. The payoff is that the cache is never stale. The cost is extra write latency, because every write hits 2 places. The best practice combines both, plus a TTL. The ElastiCache documentation calls this out directly. It says that if data is written to the cache only when there's a cache miss, that's pure lazy loading. The data in the cache can become stale, and the fix they recommend is to layer in write through and a time to live. So if a scenario worries about serving outdated data from a cache-side setup, the answer is a TTL, or combining write through, or both together. That's the official guidance. Let's take stock at the halfway mark. DynamoDB is your transactional key value store at any scale. ElastiCache is the microsecond in-memory cache sitting in front of a database. Within ElastiCache, you reach for Redis or Valkey when you need durability, replication, or rich data types, and memcached when you just want simple, multi-threaded caching. That covers running the app and making it fast. Now for the third engine, the one that answers questions over years of history. This is Amazon Redshift, a petabyte-scale columnar data warehouse built for analytics and business intelligence, and the decision rule could not be sharper. Redshift is OLAP, never OLTP. It exists to answer big analytical questions over enormous datasets, like revenue trends across years of game history. It is the right answer only for analytics, data warehousing, and business intelligence. The instant a question describes a transactional or real-time application workload, Redshift is the wrong choice, full stop. So why is Redshift fast for analytics and useless for transactions? It comes down to columnar storage. Imagine you want to total one column in a giant spreadsheet. A traditional row store is like reading every word of every page to find that one column. It touches everything. A column store is like tearing out just the revenue column and adding it up, skipping all the data you don't need. Redshift layers massively parallel processing and compression on top of that, so it splits the work across many nodes at once. That makes summing revenue over billions of rows fast and cheap on input-output, but that same design is terrible for updating a single row, which is exactly why it's an analytics engine, not a transactional one. Amazon Web Services describes the engine this way. Redshift uses massively parallel processing, columnar storage, and data compression to efficiently process complex analytical queries over very large datasets. Notice every phrase points at analytics, complex queries, very large datasets. There's nothing in there about fast single record reads or writes, because that's not what it's for. This is the language of a warehouse, not a live application database. A few integrations round out the picture, and they map to common keywords. RA3 instances separate storage from compute, so you can scale each one independently instead of paying for both together. Spectrum lets Redshift query data directly in S3, without loading it first, no extract transform load step required. So you can keep your hot data in Redshift and years of cold history cheaply in S3, then query across both in one statement. And when the product team wants dashboards, QuickSight visualizes the analytics into business intelligence reports. So remember, query S3 from the warehouse means Spectrum, and visualize the results means QuickSight. Beyond these three, Amazon Web Services offers a purpose-built database for each data shape, like a toolbox where you don't drive every screw with a hammer. DocumentDB is a MongoDB-compatible document store. So when a question says MongoDB, that's your match. Neptune is a graph database for relationships and connected data, powering recommendation engines and fraud detection. Keyspaces is a Cassandra-compatible wide column store that speaks Cassandra Query Language, or CQL, and TimeStream is built for time series data, like Internet of Things sensor readings streaming in over time. The exam tests this as keyword matching, so anchor each one: MongoDB to DocumentDB, Graph to Neptune, Cassandra to Keyspaces, Time Series to TimeStream. Here's the mistake to watch for, because it's the most expensive one. Engineers see the words big data and instinctively reach for Redshift, but big data does not automatically mean Redshift. Redshift is only for analytics and warehousing. If the workload is operational, serving active users, reading and writing individual records, it stays on DynamoDB or RDS, no matter how much data is involved. Pick Redshift for a transactional workload and you'll get slow queries and a bill that can triple compared to the right tool. Let's clear out the wrong mental models. First, DynamoDB cannot do analytics, it's strictly transactional key value, so anything framing it as the reporting solution is wrong. Second, ElastiCache is never a primary database or system of record, it's a caching layer, and the durable truth lives elsewhere. Third, don't think of DynamoDB and Redshift as rivals, they're not competing options. DynamoDB is the system of record running the live app, Redshift is the system of insight analyzing it, and mature teams run both side by side. And finally, Redshift is useless for single-row inserts and updates, so never use it as a transactional database. So here's how CodeGorillas actually wires it up. At the top, the gaming app. Player scores flow into DynamoDB, which handles the writes and reads at single-digit millisecond latency, at any scale. The real-time top ranking is held in ElastiCache, using Redis sorted sets, so the leaderboard itself comes back in microseconds. And then, on a separate path, the historical game data feeds into Redshift, where the product team runs their weekly revenue analytics across years of history. 3 engines, 3 jobs, and notice that RDS, which would have buckled trying to do all of this alone, isn't in the picture at all. Let's compress all of this into a keyword cheat sheet you can run on any question. Serverless NoSQL, single-digit-millisecond, key value, that's DynamoDB, microsecond latency, in-memory, session store, or reduced database load, that's ElastiCache, data warehouse, business intelligence, or analyze across years, that's Redshift, and for the purpose-built family, MongoDB points to DocumentDB, Graph points to Neptune, Cassandra points to key spaces, and time series points to time stream. Memorize these triggers and most questions in this domain answer themselves. Let's lock in the takeaways. First, split every question with a transactional versus analytical test. DynamoDB is OLTP, Redshift is OLAP second, ElastiCache is a caching layer and never the system of record. Third, DynamoDB capacity is a cost choice, on demand for spiky traffic, provisioned for steady, and the latency is identical either way. Fourth, cache aside loads on a miss and can go stale, while write-through stays fresh but costs an extra write. And fifth, match the keyword to the purpose-built engine. Now let's see how well you absorbed all of this with a quick 5-question quiz. Let's test what you've learned. A gaming company needs a database for a real-time leaderboard that reads and writes player scores millions of times per second, with consistent single-digit millisecond latency and no servers to manage. Which service fits best? Is it A, Amazon Redshift, B, Amazon DynamoDB, C, Amazon RDS for PostgreSQL, or D, Amazon ElastiCache as the system of record? Pause here if you want more time. This one is B, DynamoDB. It's the serverless NoSQL key value store built for single-digit millisecond latency at any scale, a textbook fit for a high-velocity gaming leaderboard. Redshift is for analytics, RDS would buckle at that right velocity, and ElastiCache is a cache, never the system of record. Question 2. A product team wants to run complex analytical queries over years of historical sales data to spot revenue trends, then build business intelligence dashboards. Which service is purpose-built for this? A, Amazon Redshift, B, Amazon DynamoDB, C, Amazon ElastiCache for Redis, or D, Amazon Neptune. Lock in your answer before I give it away. The right call here is A, Amazon Redshift. It's the Columnar, massively parallel data warehouse built for analytical queries over very large datasets, and it pairs natively with QuickSight for dashboards. DynamoDB can't do analytics, ElastiCache is a cache, and Neptune is for graph relationships. Question 3. A web application has highly unpredictable, spiky traffic, and the team wants to avoid capacity planning and user-facing throttling. Which DynamoDB capacity mode should they choose? A, provisioned mode with no auto-scaling. B, provisioned mode with reserved capacity. C, on-demand mode. Or D, on-demand mode because it delivers lower latency than provisioned. Think about which constraint matters most here. It has to be C, on-demand mode, and here's why. On-demand is pay per request with no capacity planning, and it absorbs sudden spikes far better than provisioned. Watch out for option D, it's a trap. Both modes deliver the same single-digit millisecond latency and the same service level agreement, so the choice is about cost and effort, never speed. Question 4. An application repeatedly reads the same product catalog data from RDS, driving up database load and latency, and the team needs microsecond response times for those hot reads. What should they add? A, Migrate the catalog to Amazon Redshift. B. Replace RDS with Amazon DynamoDB. C. Add a read replica and route all reads to it. Or D. Add Amazon ElastiCache in front of RDS. Got your pick? Let's see. If you said D, well done. ElastiCache is the in-memory caching layer that sits in front of RDS, absorbs those repeated hot reads, sheds database load, and serves the data in microseconds. The keywords microsecond latency and reduced database load point straight to ElastiCache. A read replica helps with scale but won't hit microseconds, and the cache stays in front of the database, never replacing it as the system of record. Last one. Question 5. A company is migrating an application that stores connected data and needs to traverse relationships for a fraud detection and recommendation engine. Which purpose-built database fits? A. Amazon Keyspaces. B. Amazon TimeStream. C. Amazon Neptune. Or D. Amazon DocumentDB. Run the keyword to engine rule before you answer. The answer is C. Amazon Neptune. The keywords connected data and relationships point straight to a graph database, and Neptune is purpose-built for exactly that. Fraud detection and recommendation engines are its classic use cases. Keyspaces is Cassandra-compatible wide column, TimeStream is time series, and DocumentDB is for MongoDB-style documents. Done with NoSQL, caching, and warehousing. DynamoDB, ElastiCache, and Redshift. If you're following the Amazon Web Services Certified Cloud Practitioner Exam Mastery in order, you've just cleared one of the steeper hills, onward and upward.